Okay, this is the last video in this chapter. So we will make the analysis more realistic by considering a weighted portfolio. Earlier, I just simply considered x equals to a plus b. But in practice, you can fine-tune the ratio, the proportion of two assets, A and B. So for example, you have to consider something like this. 30% of your money is invested in A, and the other 70% is invested in B. So your portfolio can be written as 0.3 times A plus 0.7 times B, right? So we will study how the standard deviation of or the variance of X behaves under different combinations, different weights. And remember, we will be using these formulas for the linear transformation. You may remember them. So variance is affected by a squared, but not affected by b. And covariance is multiplied by the multiplications a and c, but not by b and d. And summation is like the variance of the sum is the sum of the variances plus 2 times covariance. So remember these three formulas. We are going to use them step by step, so it might be a little more complicated. So okay, let's think about this. First, we use the variance of we will in the end we hope to calculate variance of x. But remember, x is summation of this plus this. So I can divide x into this and this. So variance of sum is sum of variances plus 2 times this covariance. The covariance between the first part and the second part, right? And then using the first two formulas, so we can rewrite this variance into square of 0.3 times variance of A. And also 0.7 inside the variance will affect the variance by 0.7 squared. So these two can be converted this way to the original variances. So these variances can be found from the data. We know how asset A and asset B behave from the data. And covariance can be also written this way. Multiplication of 0.3 and 0.7 and then original covariance. Right? Right? And then in the end, combining all the things, we have a very complicated formula for the final variance. So the variance of weighted portfolio is weight squared variance of the first asset and the weight squared and the variance of the second asset plus 2 times weight covariance. Complicated, right? But just take time and see it step by step and see if there's any missing piece. Actually, it's just tedious algebra. This is a generalization. So that was an example. Now, just we would like to set the weight on A as W. W is invested on A, and 1 minus W is invested on B. Earlier it was 0.3, 0.7, but now in general W. In the end, we would like to find the optimal W that minimizes the risk. So then following the same steps, you can write it this way. The variance of the weighted sum is weight squared variance of A, weight squared variance of B, and 2 times weight covariance. Okay, structure is identical. And this is one of the very fundamental formula for optimal portfolio theory in financial economics. As I said, we would like to minimize the risk, right? And I will consider this problem in real data. I am going to consider companies, four different companies, like from 1986 through 2016, like nearly 30 years data from Yahoo. And this is covariance matrix. You know how to interpret this, right? So let's first look at the diagonal terms. What's interesting here is Apple has the, by the way, diagonal terms are variances, remember? They are variances, and Apple has the highest variance. That means Apple increase may be the most. So the returns are very, very large, so very risky. And on the other hand, Exxon is most like a safe, reliable, least risky asset among these four. So Exxon, Walmart, Microsoft, and then Apple. That's the order of smallest risk to the largest risk. And I am going to consider a portfolio that invests 50% on Excel and 50% on Apple. By the way, we did not read these covariances. If you read these off-diagonal elements, what's interesting here is there is no negative correlation. As I said, it's nearly impossible to find negative correlation among major assets. So we have these covariances, all the positive covariances, all the stock markets move together. When the market goes up, almost all the assets follow. Okay, but now let's consider this portfolio and calculate its variance. Not a big problem. So your portfolio X is 50% Exxon and 50% Apple. And then using what we have done, so the variance of ExxonMobil was 8.03. You take this, and Apple's variance is 38. So you plug that in here. And their covariance is 3.03. So as a result, you plug in 3.03 here. So you know this, you know this, you know this. So you know all the numbers. Just calculate. In the end, surprisingly, the variance is, excuse me, what I'm doing. Oh, I'm sorry. I skipped like multiple slides at once. So like plug in the number variance of Exxon, variance of Apple, covariance between them. We know those numbers. So you plug in them, then you get 13.11. 13.11 is the variance of this portfolio, which is riskier than Exxon only. Yeah, if you invest 100% on Exxon, your risk would be 8. But now, because of the 50% in Apple, the risk is greater than Exxon 100%. But it's safer than this risk is smaller than Apple 100%. So 50-50 portfolio is in between these two guys. Okay? Now, it's your turn to calculate the variance for a different portfolio. Now consider 80% on Exxon and 20% on Apple. What is the variance of the weekly returns of that portfolio? Okay, so the idea is the formula is the same. We are going to use weight squared variance of a single asset, weight squared of the variance of the asset, and then 2 times weight covariance. You know this variance, this covariance as before. Just the only difference is the weights, 0.8 and 0.2. And then surprisingly, this portfolio returns a risk of 7.64. What's surprising here is this risk is even smaller than the smallest risk, Exxon. So you are investing on 2 assets and they are positively correlated. Still, by splitting optimal amount, optimal portfolio can give you even better, even less riskier asset than both of them. So combination of two assets can be dominating than both of them, right? So this is the magic of portfolio management, right? By the way, this is a super simplification. The real financial portfolio theory will be more complicated because you have to additionally consider expected return. I only consider the variance because it's application in statistics. But in real finance, of course, it should be more complicated, and you have to you have to mix more stocks, and like there are more things going on. But just a simple numerical example, we can show that making a portfolio can strictly better off than the original single assets. Okay. Finally, again, I am telling you everything we just considered assume linear relationship. Non-linear relationship is excluded. We did not consider at all. So your analysis could be misleading if your data have nonlinear relationships. So before using those analysis, make sure your data have a linear pattern. Or if you see a clear nonlinear pattern, then you have to study more about nonlinear analysis methods. Okay, this is it. Thank you for watching, and next chapter is the last chapter of this semester. So today it is more like a preliminary for the last one. Okay, see you in the next one. Bye.